Hi, my name is Joel Amidon, and I'm an associate professor here in the Department of Education at the University of Mississippi. Just here to offer a little video, little tutorial on moving multiplication problems from concrete, so numbers that you can touch and feel, to more abstract, so think like more flashcards. All right, so we're going to start with a simple problem. So 9 times 6. Now, some of you, when you see something multiplied by 9, you've been taught a finger trick, okay? And so how the finger trick works, for those of you that don't know, is I've got my fingers out and I know I need 6 groups of 9, and so I'm gonna say 1, 2, 3, 4, 5, 6. Put that one down. I have 5, I have 4, 54, and 54 is the answer. So I can be really happy I got the answer. But that's fine. It does work. It gives you the answer, but is that the point? Is the point to have the answer? Is the point to understand that we're talking about 6 groups of 9 or 9 groups of 6? And what does that look like physically? What does it look like as an area? What does it, what do those numbers actually mean? Rather than just memorizing a trick. So there's nothing wrong with the trick. It gives you the response, but maybe there's something wrong. It doesn't lead to understanding. Okay, so that's what we want to do. We want to lead from understanding. We want to do something that's tangible. So something that, say, is concrete. I could also say I want to do something that's using direct modeling. Okay, so something concrete or something with some direct modeling. So if I'm thinking about, hey, I've got 9 buckets and 6 apples in each bucket, how many buckets do I have? I mean, you could go and, well, you could get really tangible. You could grab and get, whatever I said, 9 buckets, right? Actual buckets. Right, or something like, like this, a tub of some sort or a little dish of some sort, and put 6 things into each, and then have the child count them all out. That would be really concrete. They would really have to understand. They would see what 54 looks like. They'd also be counting a lot. Or you could switch that around and say, I've got 6 buckets with 9 apples in each. Again, they're having to do the put them out into each thing, have to count them all out. That would be direct modeling. They're very concrete, right? Another way to do that could be to take something like these chips, hold them up for you, chips, right? And we could lay them out on a flat surface, so 1, 2, 3, 9 across, 6 down, and count those out, right? That'd be another way to get really concrete, so you can actually touch and feel the numbers. Another way, so we can move down from a little bit more, less concrete, but still getting a way that you can count them and see the numbers, is to make a grid, right? So we could make a grid this way. We could make an array, right? So we could do 1, 2, 3, 4, 5, 6, 7, 8, 9, and do that 6 times, okay? And then we could go through and count them to make see a kind of a rectangle shape. Or let's just make a rectangle and make it into a grid, right? So 4, 6, 7, 8, and 9, and then we want to make 6 across, right? There we go. So I've got 6, I've got 9. I could count all those up and see that it's 54. Now, another thing I could do is start using something we're going to call invented strategies, right? And anyway, this is a little less concrete. It's a representation. I can still count, but I can't really touch and feel it. I can't take that apart. I can't take each of those squares out and really have a sense of the numbers, but I can see it. So it's not as abstract as just a flashcard where there's numerals, which who knows what those numerals mean, but we've got something we can actually count through. So we're still in the representational sort of stage here. So rather than counting them out, I could do something what I was going to say is called invented strategies. Invented strategies to figure out this answer. Because I don't actually, pretty soon a kid's going to say, you know what, I don't want to count out to 54. I know some things, all right? And so one thing they could know is, hey, I don't know 6 times 9, but I do know 6 times 10, right? I do know 6 times 10. So maybe they tack on another one here, and say, so we added on one more, so this is 10. So 6 times 10 is 60, right? And then they say, ooh, I'm going to take away these 6, so 60 minus the 6 I tacked on at the end to get me to 10, and that gets me to 54. Or they could even count it, so 60, so take this out, 59, 58, 57, 56, 55, 54. Alright, so still tangible, still somewhat tangible, but I can see how I'm getting to 54. Or they could also say, what's another way we could do this? Is to think like, I don't know 9 times 6, but 9 times 5, I know that one. So let's see, maybe we'll do different color here, green. So I know 5 times 6, so that would be that, or 5 times 9, right? So this would be 5 plus 1, so 5 times 9, 5, 10, 15, 20, 25, 30, 35, 40, 45, right? Kids are used to counting by 5s, and then I'm adding, so 45, and then I'm just adding one more 9. That gets me to 54. So I can add a 9 on to, or even go even further, going back to the other thing, I know 45 plus 10 is 55, but 9 is one less. Go back to 54. And some of you might be saying, that seems so inefficient. Why don't I just tell them to memorize 9 times 6 is 54, 6 times 9 is 54. There's not the number sense. And you're saying, what, they're doing a lot of math. Like, oh, they're doing a lot of math. That's not a bad thing. That's not a bad thing. They're developing their number sense. They're connecting these things together. They're seeing how far 60 is away from 54. They're seeing how far 55 is away from 54. Doing more math is not the issue, right? We want them to do this math so that eventually they get down to the point where they memorize that 9 times 6 is 54 because they've done it so much. They're playing around with the numbers. It just makes sense to them. So when I throw up the flashcard, they have a sense that I know that's 54, or they can figure it out with some of these other ways, right? But really we want them to think about this idea of multiplication as area. Like that is like a foundation for this. And just one more way, we were kind of messing around, we came up with another way here. So if I have 6 times 9, maybe I might break this down into, so I like the idea of breaking it down into 5s. I could say, well, this is 5 plus 1, and 9 is really 5 plus 4. And again, I'm just messing around here. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So this is 5 times 5. Well, what's 5 times 5? 25, right? And the kid might know that one already. 5 times 1, this little strip down here, well, that's another 5. 5 times 4, that makes this 20. And 4 times 1 is 4. 25, 45, 50, 4. That can get me to 54 as well, right? So, it seems like we're going around and around, but different ways of getting the kid to understand what this multiplication is. What does it mean to have 9 groups of 6, right? And different ways to break it down and still get to the answer. We're trying to get to this from this to this, and we don't have to take the direct shot of memorizing. We can go a little bit around in order to explore more of Numberland, right? If we explore more of Numberland, we have a better understanding of numbers, okay? And then so all these other multiplications are going to make more sense, and like addition, subtraction, I'm getting better and better at it if I do more and more of it, right? So it's okay if they're doing it. Eventually they'll get efficient. Eventually they'll know the fact, but let's move them through understanding. And also thinking about this idea of area is going to be helpful going forward. So maybe it gets a little bit harder than 9 times 6, and we're talking about 12 times 22, right? A little bit harder, right? 2-digit numbers. And so we're going to still think of it like area, but maybe we don't have to make the whole grid. Instead, let's maybe think of 12 as 10 times 2, and 10 plus 2, and 22 as 20 plus 2, right? And so 10 times 20, 200, 20 times 2, 40, 10 times 2, 20. 2 times 2, so where the row and the column meet is where I'm multiplying. It's 4. And now I just add them up. 200, I got 40, I got 20, and I've got 4. 4, 6, 264. Now some of you might say, hey, I would just stack them and multiply them, which is the same, and actually we did the same exact stuff doing this. So 22 times 12, 2 times 2 is 4, right there. Okay, 2 times 2, but it's not 2, it's a 20. So that would be 2 times 2, 2 times 20, it's 40. Right? Right there. 10, this is not, so we're moving over, right? And why are we moving over? Because they're not multiplying by 1, we're multiplying by 10s. So 10 times 2 is 20. And then 10 times 20 is my 200. So you see, all these steps I'm doing within this grid, but it makes a little bit more sense here, and I could lay it out like a grid, and so we could see that, but I don't necessarily need to. This is not bad. We're not saying that the standard algorithm is bad. It's just saying that it's built to be efficient, and we might not necessarily need to be efficient right now. Okay? They'll teach this. They're going to teach this eventually, but make sure we have this area model understood, because it has value beyond just multiplication. Don't just discount it because you don't say, oh, it's inefficient, you're using a lot of space on the paper. Let's hold off, because what if instead of 2-digit numbers, you had 3-digit numbers, boom, you could still expand out. So like 312 would be 300 plus 10 plus 2 times by 20 plus 2, say 312 times 22. You could still just expand out that area model. Area model still works. Another thing we could do is thinking about x plus 2, x minus 2 in an area model. Now, we would see this in algebra as x plus 2 times x minus 2. And you remember what we would do? We would do something called FOIL, right? First, outside, inside, and then last. And you multiply all those things out, which is fine. It works. It works for only when we've got, FOIL works for only when we have a two-term polynomial and a two-term polynomial being multiplied by each other. You could also use that in an area model. So where they meet, I don't have to remember what F, O, I, and L stand for, just where the rows and the columns meet, I multiply x times x squared, x times positive 2 is 2x, x times a negative 2 is negative 2x, right? X, positive 2 times a negative 2 would give me negative 4. So now, and I see that those cancel out, I get x2 x squared minus 4. Anyway, you could, however long these terms are, you could just, again, expand out the rectangle, right? If it's 3 terms, make it 3 wide and 2 deep, and it'll still work. So this area model has legs, and thinking about multiplication as area goes beyond learning something like 9 times 6. So let's really embrace the area model as we go from concrete to abstract. So numerals are abstract. You didn't know what this circle with a stick on it represented 1 less than 10. You didn't know that until you were taught that. And so making sure that we understand that this is abstract. We don't see anything that represents what these numbers are, so we want to make sure it's rooted. The foundation is understanding that these numbers represent an array, represent rectangle, represent area. So I have something concrete attached to this fact in my head. So let's build the facts, or let's build the facts with concrete knowledge, representational knowledge, and then when we get there, we really understand it. We're not just memorizing something. Okay? So if you have any questions about this, you can hit me up at my Ole Miss email at jcamidon@olemiss.edu, or you could hit me at joel@amidonplanet.com. Thanks.